a battery that charges faster the bigger it gets. Every battery you own works the opposite way. Last week, Australian physicists broke that rule entirely. The quantum leap. Today, we trace a convergence, reshaping energy storage forever. Here at the Quantum Leap, we map where breakthroughs collide. Quantum physics, solar science, and materials engineering just intersected unexpectedly. The result challenges 2 centuries of battery chemistry assumptions. And the implications reach into every power grid on Earth. First, we need to understand why chemistry hit a wall. Every battery on Earth stores energy through chemical reactions. Lithium ions shuttle between electrodes, storing and releasing electrons. The principle is fundamentally unchanged since Volta's pile in 1800. 2 centuries of refinement, same underlying physics, chemistry. Chemistry gave us smartphones and electric vehicles, real achievements. But chemistry has hard limits that no engineering can overcome. Chemical reactions generate heat. Heat degrades materials. Materials fail. Push charging speed higher, and degradation accelerates exponentially. Scale up the battery, and charging time increases with it. This is the fundamental constraint. Chemistry scales slowly. Sodium-ion batteries entered the market promising cheaper grid storage. Solid-state batteries promised faster charging with less fire risk. Silicon anodes offered 20% more energy density per kilogram. Real progress, genuine improvements, all within the same paradigm. But what if the paradigm itself is the constraint? In March 2026, a Melbourne team asked something different. What if energy storage does not require chemistry at all? Dr. James Quach led the team that answered it experimentally. The paper published in Light, Science and Applications proved it. Energy stored not in chemical bonds, but in quantum states. Now we know the stakes. Let us examine the science. Quantum mechanics describes energy in discrete steps, not smooth gradients. An electron occupies one level or another, never in between. Pushing an electron up requires energy matching the gap exactly. A wrong energy photon passes through entirely, no partial absorption. This selectivity makes quantum charging fundamentally precise and controllable. The CSIRO team built their battery around this principle. 2 layers inside a microcavity. One charges, the other stores. The charging layer uses a phenomenon called superabsorption. Molecules absorb photons collectively, not individually, faster together than alone. This is the core paradox. More molecules means faster charging. In classical batteries, adding material slows every process down. In quantum systems, adding material accelerates collective absorption exponentially. The paper calls this super-extensive charging. The physics is peer-reviewed. But charging is only half the problem. Storing is harder. Excited electrons want to fall back immediately. Nature demands relaxation. Previous quantum batteries discharged as fast as they charged. Useless. The Melbourne team solved this with an elegant molecular trick. They added a second layer using palladium tetraphenylporphyrin molecules. These molecules trap energy in what physicists call triplets. Which field breaks through next? Share your prediction below. In triplet states, electron spins a line in one direction. Quantum rules forbid the transition back. The energy stays locked. Physicists call these dark states. The atom cannot emit. No emission means no spontaneous dumping of stored energy. Here is something remarkable. You have witnessed this physics daily. Every flame is quantum energy storage happening in reverse. Electrons fall back, releasing photons. Specific colors, specific gaps. The quantum transitions making fire glow now store energy. The science was always visible. We learned to engineer it. The CSIRO prototype achieved storage lasting 40.3 microseconds. That sounds small, a 1,000-fold improvement over previous attempts. The honest assessment: microseconds remain far from practical energy storage. Daniel Tibbon says 1 second of storage is theoretically achievable. The gap between microseconds and seconds, 6 orders of magnitude. We present this with the epistemic honesty the science demands. The proof of concept is real, deployment remains far ahead. But here the story becomes something no field predicted alone. While quantum batteries advanced in Melbourne, Japan broke through. Same week, same quantum physics, completely different application. So far, these look like parallel developments. They are not. Singlet fission, a quantum process doubling photon energy from sunlight. 1 photon enters a specially designed crystal. 2 excitons emerge. Researchers in Japan achieved 130% quantum yield. Published in the Journal of the American Chemical Society. A molybdenum spin flip emitter capturing multiplied triplet energy worked. Triplet energy, the same state quantum batteries use for storage. 2 teams on different continents exploiting identical quantum physics. Neither team cited the other. The convergence was invisible. Our analysis reveals something neither field has fully articulated. Perovskite crystals appear in both solar cells and quantum batteries. The same materials revolution, driving solar feeds quantum storage. Not coincidence, a convergence with deep structural foundations beneath it. When shared material platforms emerge across fields, adoption cascades. Lithium-ion followed this path. Perovskite manufacturing scaled for solar first. That infrastructure now becomes available for quantum energy storage applications. University of Adelaide researchers have already proposed integrated solar quantum devices. Harvest sunlight and store it quantum mechanically, 1 device. No separate battery bank, no wiring between panels and storage. The most significant energy convergence since lithium-ion met portable electronics. That assessment is ours. The market has not priced this. Quach earned 3 degrees before finding quantum physics. Computer science, engineering, commerce. Then he went back for physics. Marie Curie Fellow, Tokyo researcher, then CSIRO science leader. The breakthrough required someone who could think across disciplinary boundaries. His team now chairs the International Conference on Quantum Energy. The field fits in 1 conference room. That will change. Meanwhile, Cambridge overturned another assumption about energy storage entirely. Disordered supercapacitor materials store twice the energy of ordered ones. Order was supposed to be better. The data says otherwise. Cross-reference quantum battery research, and a pattern emerges clearly. Collective quantum effects thrive in classically imperfect conditions. Molecular disorder enables quantum order. A productive paradox emerges. In our assessment, the most underreported convergence in energy science. 3 models predict different timelines. Honest answer: nobody knows yet. But the trajectory of the underlying science is accelerating measurably. When reviewers checked this paper, they verified methodology twice. The results held, peer-reviewed, replicated across 5 prototype configurations. The physics is established. The engineering challenge begins now. The question is no longer whether quantum energy storage works. What does this mean for our grids and for civilization? If quantum batteries scale as the physics predicts, economics invert. Bigger installations cost less per unit of charging speed. They would cost less. Quantum collective effects reward scale. Solar panels generate power only when the sun shines. Integrated quantum solar devices would eliminate the storage bottleneck entirely. Capture and store in one step, no conversion losses. We must emphasize, this remains decades from grid-scale deployment. Timelines in emerging technology are notoriously unreliable on both sides. What matters is not the date but the trajectory. And the trajectory across 3 fields simultaneously bends toward convergence. Iron-air batteries now provide multi-day grid storage commercially. Sodium-ion cells deploy today in China, America, and Germany. Perovskite silicon tandem solar cells approach 34% efficiency commercially. Each advance creates conditions for the next convergence to emerge. The framework: when cost thresholds cross simultaneously, adoption cascades. Solar crossed its threshold in 2015. Genome sequencing in 2020. Iron-air batteries are crossing theirs now. The question is quantum. Any channel promising quantum batteries in 5 years sells certainty. The science has not earned that certainty. Researchers confirm this. What the science earned is serious, sustained, funded attention. The full paper is published through Nature's Journal Family. Dr. Quach's team plans next-generation designs with extended storage duration. If storage reaches seconds, then minutes, the game changes. That conditional matters, if not when, we track trajectories. The technology that stores energy without chemistry fundamentally exists now. Quantum states making fire glow now hold energy for microseconds. Tomorrow it may be seconds. The physics permits this scaling. Quantum batteries will not replace lithium-ion, not the point. They open a parallel pathway, physics alongside chemistry, both serve. The convergence between quantum storage and solar changes everything. Not just grid architecture, how we think about energy itself. Chemistry asked, store more energy in ever smaller spaces. Quantum physics asks, make storage intrinsic to the material. That reframing is the real breakthrough. The device proves it. We do not know the timeline. Researchers are honest. The physics works. The proof is real. Trajectory accelerates. A battery charging faster when bigger. Remember that paradox. The future does not arrive at once. It arrives convergent. Which convergence reshapes civilization next? Share your prediction below. Next week, the convergence between AI and drug discovery. The timeline just accelerated. Subscribe to track it with us.